Hello, everyone, and welcome back. So today's topic is Taylor series expansion. And when it comes to quant finance, Taylor series is probably the most important weapon in your arsenal. Okay, I can't even begin to explain how powerful this tool is in all of quant finance. So yeah, you will be using Taylor series, pretty much for everything going forward. So this session is extremely fundamental. So let's understand the maths behind this. Maths is simple, not complicated. We'll do a couple of problems to understand the application, and I have some cool visuals also to show you that how it actually works. Okay. All right. Before we start, there is a question. One quick question: what are the different types of differentiation? Okay. Yes. So the differentiation that we have done so far is called ordinary differentiation. Okay. And equations involving ordinary differentiation are called ODEs, ordinary differential equation. That involves symbols like this, dy by dx, ordinary differentiation. Okay. And we do this when there is only one input variable, right? So y is a function of x, just one x. Derivative of y with respect to x is ordinary derivative because it's just one variable. So do the ordinary differentiation. Okay. And any equation that involves these kind of derivatives is called an ordinary differential equation. We'll have a separate session on that, right? So let's say dy by dx plus double derivative d square y by dx square equal to 5. This is the ordinary differential equation, ODE. Then you have functions of multiple variables. So this question is very relevant because there is Taylor series expansion in for univariate functions. That is what we will do today. Later on, we will revisit Taylor series again when we do multivariable calculus that involves functions of multiple input variables. Okay. When you have multiple variables, so let's say z is a function of x and y, two input variables. So which is typically the case in our world of finance because you deal with derivatives, which are price of derivatives are functions of multiple input variables, right? Then you cannot, so when you differentiate with respect to one variable, you have to keep the other variable constant. There we have partial derivatives. So we write del z by del x or del z by del y, right? These are partial derivatives. Okay. Um, yeah, so pretty much these are the two types of derivatives. When it comes to differential equation, you have ODE, then PDE, which is this one. And sometimes you will have this special term, DW, which is the Brownian increment. Whenever we are dealing with this, whenever you find this in the equation, it's called stochastic differential equation because then that starts involving random variables. Up until this, there is no randomness. It's all deterministic function, y equal to x square or y equal to log x. Everything is deterministic. The moment one of the variables becomes random and functions of those variables become, again, random variables, right? Normal distribution kicks in, and then we have a whole new different branch of calculus called as stochastic calculus. There you will see this guy, dw. Okay, some people write dv, Paul Wilmot writes dx. Again, that's for later. But yeah, to give you a high level, so this is the distinction. I hope I answered your question for now. Okay, let's move on then. So we have Mr. Brooke Taylor, okay, and he gave us the Taylor series expansion. Um, yeah, so there is another series called Maclaurin series. Initially, when I taught Taylor series, I thought I don't know why Maclaurin series came before Taylor series, but that's not the case. There is Maclaurin series is a special case of Taylor series. It is not a new invention. Okay, Taylor series came first, which is the most general application of approximating a function locally. That is what we'll see today in detail. Maclaurin made use of Taylor series specifically at x equal to 0. Okay, and it got a separate name, Maclaurin series. But the Maclaurin series is a special case of Taylor series. Okay, we'll see that in detail. All right, let's proceed. Okay, so Taylor series or Taylor expansion of a function is an infinite polynomial representation. Polynomial representation, right? You remember polynomial? You have only powers, x square, x cube, x fourth, right? No sin x, no log x. So you're given any kind of function, f of x, it can be expressed as an infinite polynomial where the coefficients of the polynomial are related to the derivatives of that function at a given point. So that's the idea, right? Taylor series expansion, let me repeat, is of a function is an infinite polynomial representation where the coefficients of the polynomial are linked to the derivatives of that function at a given point. Okay. Now, mathematically, it looks like this. So we have a function f of x, and on the right-hand side, we have a polynomial representation because there is a constant term, and then the coefficient and linear term, and another coefficient, quadratic term, then another coefficient, cubic term, blah, 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 nth coefficient, nth power, and it goes on. It's an infinite polynomial. Okay. And when we write it in this form, you see it is not just x, x square, x cube. I have written it as x minus k whole square. So this form we develop when we are trying to expand the function at a specific point x equal to k. Okay, we'll understand all of these. What is expanding at a particular point actually means. But this is the form, okay? Any function, if you want to expand at a particular point, you write it in this form. Okay, now this is in general, right? You have f of x and then you have a general representation on the right-hand side. Now, given a specific function, let's say log x or sin x or e to the power x, you can specify the exact polynomial. These coefficients that we have, a0, a1, a2, etc., you will be able to calculate those. And these will be nothing but quantities which are related to the derivative of the function f of x. Okay. All right. We'll derive all of these slowly and steadily. Don't worry. So this is the form that you need to, this is the most general form, expanding f of x at x equal to k. This is how you need to write the equation. Everything else follows quite naturally after this. Now, as I mentioned, right, if you are trying to expand at x equal to 0, that's a special case. So k is 0. Then you get this expression because k is 0, so you get a0 plus a1x plus a2x squared, blah, 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 blah. This is called as Maclaurin series, which is a special case of Taylor series. Okay, Maclaurin series came after Taylor series. So you see, this is more general. Because it involves some parameter k that I can change. And this is specific to k equal to 0. All right, and it is fundamental for in all of quant finance that you will see. So this, I mean, Taylor series expansion is something you'll be writing, I think, probably 1,000 times in the entire course. Any questions on this slide? Are you okay with the form, the representation, coefficients, powers, right? Okay. Yes, so I can expand it at any point x equal to k. In Maclaurin series, that special point is at x equal to 0. That's the only difference. All right. Now, how do we derive this? Suppose, so we write, so let's first, okay, yeah, let's take this general form, f of x equal to this. Our objective is to find out these coefficients. How do I find out these coefficients? First and foremost, Actually, yeah, this slide is taking all the fun out of it. Let me not show you everything. So we start with this formulation. Constant term, linear term coefficient x minus k, then a2 x minus k square plus plus plus. Nth term would be an x minus k whole to the power n, and it goes on. Our objective is to find out the coefficients. How do I find a0? There is a trick. This function would be given to you, some known function, right? How do you find the a0, which is the constant coefficient? Any ideas? Okay, you're saying x equal to k. That's correct. Put x equal to k. Left hand side becomes f of k, right? Value of the function at x equal to k. Right hand side becomes a0. How nice. Everything else is just 0. Okay, value of the polynomial at x equal to k on the right hand side doesn't matter if it is infinite. It's just a0. And value of the function at x equal to k is f of k that you can calculate. If I give you the function, you can calculate. So a0 must be equal to f of k. This is nice. How do I calculate a1? The beauty of polynomial is if you keep differentiating, right, the power of x reduces one by one. X square becomes 2x, right? X cube becomes 3x square. And you differentiate again, 3x square becomes 6x. Differentiate again, it becomes 6. So power comes down. So think like this. We can pretty much make every term become a constant like a0 by successive differentiation, yes? So as Mridul said, differentiate the function on the left hand side, right hand side once with respect to x. We get f dash x is equal to derivative of constant is 0. We have a1. Derivative of x minus k is just 1 plus 2a2 x minus k plus blah blah. And then what do? Again, put x equal to k. So we get derivative of the function at x equal to k, f dash k is equal to a1. All other terms will vanish because x equal to k. Make sense? Any questions? Okay, no questions. How do you find a2? Let's do one more. How do you find a2? Differentiate twice. We know the pattern, right? If you differentiate twice, what will happen? Can I move this here? No, sorry. Okay, if we differentiate twice, what will happen? F double dash x is equal to first term, second term will vanish. This will be differentiated twice, which will be 2a2. That's it. Plus the next term is, I'm doing it in one shot, okay? 3a3 square, then 6a3 x minus k. Right? And then you put x equal to k, you get f double dash k is equal to 2a2. So a2 is half f double dash k. All right. Are you clear with this? This is how you can keep finding the coefficients one by one. Did I lose you guys? You're still there, right? Okay, cool. How do we find the general expression for this guy, an? How do you find the general expression for this? So in order to find a2, how many differentiation I used? Twice. So in order to find an, how many times I need to differentiate this guy, this entire expression? N times, right? So you differentiate the function n times, that will give you all these terms before this point would have vanished. This would be the first term. So after n minus 1 differentiations, all of these terms would have vanished because they are lower power than x to the power n. Only this will survive. So in the nth differentiation, what will happen to this guy? Let's see. So you understand this particular recurrence relationship. When you differentiate that particular term first time, it will be, look at this, n a n x minus k to the power n minus 1. So the original term is this. This is my original term before any differentiation. Differentiate once, you get n a n x minus k to the power n minus 1. Differentiate twice, you get n times n minus 1 a n x minus k to the power n minus 2. Differentiate thrice, you get n times n minus 1 times n minus 2 times a n x minus k to the power n minus 3. Differentiate n times, continue this pattern. What will I have here? Will not it be n factorial? Because look at this. It'll go till 1, right? And then we have a n. Third term has a n minus 3. So nth term would have n minus n. N minus n is 0. Anything to the power 0 is 1. So this is it. That's it. There is no x. X will vanish. Just at the, nth differentiation, you'll have this. So if this is the derivative, and the terms above this will contain at least one x minus k. The next one will contain x minus k. The one after that will have x minus k square. Okay. So after n derivatives, my function essentially would have become this. N derivatives of f of x is given by n factorial an. This is the constant term. Okay. And then you have beyond. I don't want to worry about those. Some kind of coefficient times x minus k, some coefficient times x minus k square. And then you put x equal to k, that will give you nth derivative of f of x at x equal to k is n factorial an. These will vanish as usual because x equal to k. And from here you get the formula, general formula for nth coefficient, which is nth derivative of the function at x equal to k divided by n factorial. That's the formula. Now, any questions? This should be crystal clear to you. Let me know if you have any hiccups. So one thing to note here is there are two ways the terms vanish. One is once you differentiate this entire function multiple times, if you differentiate this n times, all of these terms naturally vanish because derivatives, shrink the power and then they will be constant and then it will fall off, right? That is how these terms vanish. All the terms, and this one would become a constant after n derivatives. Anything above that still remains, but they remain with a term x minus k, x minus k, x minus k square, x minus k cube, and those will drop off when I put x equal to k. Okay, because they contain the term x minus. So they drop off later. And then finally, I'm left with these coefficients. So this is extremely, extremely interesting. Okay, so you're clear with this derivation? Any questions? Is there some lag, guys? I'm not seeing any response. Normally, you guys are very energetic. Okay, let me know because this topic is extremely fundamental. If you are not able to grasp the Taylor series, you'll have problems later on. All right, so this is what I have derived. Let's proceed. So just, using that formula, I have rewritten the final expression. It goes like this. Any function f of x is given as f of k, that is the constant term a0, right? And first derivative times x minus k, second derivative by 2 factorial x minus k square. Nth term is nth derivative at k divided by n factorial times x minus k to the power n. Remember, these terms are always there. We were just trying to find out the coefficients and we found them, right? Then we reconstruct the polynomial and this is what we have. In a compact way, you can write it like this, right? So nth term is nth derivative at k divided by n factorial times x minus k to the power n, and there is an infinite sum, n goes from 0 to infinity. Okay. All right. Now, if you want to get the Maclaurin series, just put a k equal to 0 because this the expansion is around 0. So if you put x equal to 0, you get f of x equal to f of 0, f dash 0 times x because k is 0 everywhere, right? F double derivative at 0 divided by 2 factorial x square. Similarly, you have this one. And then in the compact form, you can write it like this. Okay, k is replaced by 0 and all x minus k's are replaced by x because k is 0. That's it. So this is our infrastructure for today. Now, using this, you can do a lot of things, a lot of things. Let's proceed. Let's do some quick exercise. First and foremost, so what does it say? Write Taylor series expansion for e to the power x, expanding at x equal to 0 and x equal to 2. Let me do it here, and then we'll write the result. Okay, question number 1, expand e to the power x. So how you proceed with this is, basically you know the general formula, right? So you can write it like this. This is equal to, okay, let me do this. Expand at x equal to 0. You can use the formula or you can do it all over again. It's good to practice, okay? Practice the form. So I can write e to the power x is a0. If you're expanding at x equal to 0, it should be like this. A0 plus a1x plus a2x squared and an x to the power n. Okay. And using Maclaurin series or special case of Taylor series, a0 is f of 0. A1 is f dash 0 by 1 factorial times x. A2 is f double dash 0 by 2 factorial x squared. Nth term is f nth derivative at 0 divided by n factorial x to the power n. What is f of 0, guys? Value of the function at x equal to 0. 1. What is derivative of e to the power x at x equal to 0? 1, just a lot of 1, right? 1 divided by 1 factorial x. Second derivative of e to the power x at x equal to 0. Again 1, right? Always 1. 1 by 2 factorial x squared. 1 by n factorial x to the power n. So we have 1 plus x squared by 2 factorial, x cubed by 3 factorial, This is the Taylor series expansion of e to the power x at x equal to 0. Okay, I'll show you visually what it means a little later. Just do the maths for now. You have to be clear. Did you understand this derivation? Any questions? Others? Anybody new to Taylor series? Like first time they're seeing this? Okay, cool. Now question 2 was expand at x equal to 2. So not at 0. How do we do this? There are two differences, remember. One is the form is different. Do not write a0 plus a1x plus a1x square, a2x square plus a3x cube. That form does not exist. Form is different. The form is this, a0 plus a1x minus k. Remember? a2x minus k square. Okay. Nth term is an x, oops, x minus k whole to the power n. This is the form. The form is different and the coefficients are different. For the coefficients, the general formula is an is f of n at k, in our case it will be 2, divided by n factorial. Right? That's it. That's the coefficient. So in my case, the A0 would be, it is not f of 0, it is f of k, correct? So it is f of 2 plus a1 is first derivative at 2 divided by 1 factorial times x minus 2, not x. The form is different, okay? A2, for A2, what should I write? Double derivative of f at 2 divided by 2 factorial, x minus k whole square, right? This is how it goes. F of 2 is e square. Derivative of e to the power x is e to the power x. Again, you put 2, so that is also e square. This is always e square, right? That is how it goes. Nth term would be, again, e square by n factorial x minus 2 whole to the power n. This is expanding e to the power x around x equal to 2. Okay, are you clear with this? One more example. Let's do a couple of more examples just to get some practice. Second one is, okay, before that, there is a question. Just can you explain F2 a little bit slow? Okay. Let's go back to the derivation. See, this is the general expression. And this is special. In the second question, we are doing the general expression, right? If you look at the expansion, f of x is f of k plus f dash k times x minus k, right? So e to the power x is e to the power 2 because we are expanding at x equal to k equal to 2 in this case. And then it goes up. In the second case, k equal to 0, so you had 0 every f0, f dash 0, f double dash 0. In the top one, you have fk, f dash k, f double dash k. K can be anything. Okay, that's the difference. Cool. Second question was around log 1 plus x. This is an important expression. See, in all of quant finance, you don't need really that many trigonometric functions. It will be mostly polynomial, exponential, log. That's all. Sometimes, there will be some kinky functions like, heavy side function or modulus sometimes. We'll get to that later. So the next question was log 1 plus x, right? expand at, I think it was at x equal to 0. Yeah, expand at x equal to 0. You can also expand at other values, but now let's write a few derivatives. F dash x is 1 by 1 plus x. Double derivative is minus 1 by 1 plus x whole square. Triple derivative is 2 divided by 1 plus x whole cube. Let's write one more. Fourth derivative is minus 2 times 3, right? That is 6 divided by 1 plus x to the power 4. Okay. So we write Maclaurin series f of x equal to constant term, derivative at 0, linear term by 1 factorial, double derivative at 0, quadratic term, 2 factorial, triple derivative at 0, cubic term, 3 factorial, etc. What is log, what is the value of the function at x equal to 0? Guys, Sachin says 0. Everybody? Log 1 plus 0? Log 1, 0. Yes. Derivative of, we already calculated the derivative here. Put x equal to 0, you get 1. So x divided by 1 factorial, that is x. Double derivative is here. Put x equal to 0, you get minus 1. So minus x square by 2. 2 factorial is 2, okay? Plus triple derivative here. Put x equal to 0. You get 2x cube by 3 factorial. Actually, you know what? Let me retain this for now. The next term would be, what is the next term? Let me write it down. Fourth derivative, x to the power 4 divided by 4 factorial. So that is minus 6, 6 divided by 4 factorial, x4, right? So one thing we notice is that it alternates between plus and minus, plus, minus, plus, minus, plus, minus. But you can simplify this. X minus x squared by 2 plus, did you notice that when we do differentiation, there is already a power, right? And it keeps increasing. So when you have 2 here, you have 6 here. What are these? This is actually 2 factorial, 3 factorial. Next term would be 6 times 4, which is 24. That is 4 factorial. Correct? So in the numerator, we have the factorials. Actually, in the denominator also, we have factorials. Okay, in disguise. So in the numerator, you have 2 factorial. This is 3 factorial. Okay, next one will be 4 factorial. But in the denominator, it's one higher term. It's factorial, but it's the next factorial. Okay. So if that is the case, then what happens when you have this n minus 1 factorial by n factorial? This is 1 by n. Because n factorial is n times n minus 1 factorial, the second term will cancel and you just have 1 by n. If it is 1 by n, then this is what I have. And it goes on. This is nice. So log 1 plus x is given by this. And remember when we did limits, I explained that if x is very, 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 very small, then you can forget about these higher terms. Okay, if you take a very, very small fraction, right, then the square and cube will be even much, much more smaller. So this limit, if I write limit x tends to 0, log 1 plus x becomes x. And that's why the ratio is 1. Limit x tends, if you take a very small value of x, then log 1 plus x will be same as x. Okay, we can probably quickly just verify that. So this is x, this is log 1 plus x. Value of x is, let's say, 1, and log 1 plus x is log 1 plus x. And then let's take the ratio, this divided by, or it's fine, we can compare. If I make this smaller, 0.5, they are getting close, extremely close. Okay, that's why they are same if x is small. All right, Taylor series expansion, extremely useful for evaluating limits as well. And then there is one more, which is interesting. Let's not lose sight of trigonometric functions totally. I mean, they are interesting. Sometimes you'll use it. So let's do this. Expand sine x at x equal to 0. Okay. We have question 3, sine x. F dash x is cos x. F double dash x is minus sine x. F triple dash x is minus cos x. Fourth derivative, sine x. Right? Comes full circle after 4 derivatives. Taylor series expansion would be sine x is equal to, I'm writing directly, okay? F of 0 means sine 0. Sine 0 is 0. F dash, you know what? Let me not do that stuff. This is our first time, right? F dash 0 x 1 by 2 factorial f double dash 0 x square 1 by 3 factorial f triple dash 0 x cube. F sine 0 is 0. Then cos 0 is 1. So this is x. Then minus sine 0 is 0. So there's no x square term. X cube triple derivative. This is cos 0 is 1. Minus cos 0 is minus 1. So minus x cube by 3 factorial plus it will become 0. So it will alternate. So every alternate term is 0, and then you retain the odd powers. X to the power 1 will be there. X to the power 3 would be there with alternating signs. So x to the power 5 will come. Okay. I leave the expansion for cos x to you. Okay. You'll see that all the even power uh, uh, would be retained and everything, odd powers will be all zeros. So just to clean it up, we get x minus x cubed by 3 factorial. Alternate sign, yes. Plus x5 by 5 factorial minus goes on. This expansion is also useful for stating that limit x tends to 0, sine x by x is also 1. Right? Because higher terms will vanish. It will approximate x. E to the power x also that we did. E to the power x, when x tends to 0, x is close to 0. If x is close to 0, e to the power x will become 1. Okay, but more interesting limit is this. Limit x tends to 0, e to the power x minus 1 divided by x. You can clearly see e to the power x minus 1, then divide by x will be 1. Okay, because you start with 1, then one of the x will get cancelled, and then when you put x equal to 0, you'll have 1. Everything else will vanish. Okay. Any questions? Are we clear with the exercises? Okay, let's proceed. Now, there is one aspect to Taylor series which is a little complicated, so we will not do it at the moment. It's about convergence. So there are tests to verify if this series converges. This is for information only at the moment. If the maths behind this gets complicated, there are a lot of theorems also. Right now, we are not mature enough to handle that. So we'll park it for later. So basically, if we said that f of x is given by this infinite polynomial, correct? You write till the nth term. Now the remaining terms are called as remainder. All right. Till nth term, it is a polynomial of degree n. Let's call this part Pn, the one that I've highlighted, Pn plus some remainder. Now we say that the Taylor series expansion converges if limit n tends to infinity, the remainder becomes zero. Remainder approaches zero, which means if you include infinite terms, there will be nothing remaining. The remainder will not be significant. Okay, it will be remainder is like an error. Error term should go close to zero if you include more and more terms. You keep increasing n means the degree of the polynomial, the number of terms that you're considering is more and more and more. If the remainder shrinks to zero, then we say the series converges. It is not always true that all functions at different points will always converge using Taylor series. Most of the cases it will. E to the power x, yes. And sin x, yes, everywhere. There are restrictions for log 1 plus x. Okay. So just for extra information, log 1 plus x will converge if x is between -1 to 1, plus 1 included. If it is outside this boundary, you'll see the series diverges. The error will become more, right? It will never converge. But let's not go there at the moment. For our all practical purposes, you don't have to worry about convergence at the moment. All right. Okay. Sachin has a point. Big O notation is something I will introduce a little bit later. Today's session, we have that notation. We'll see that more and more. As you mentioned, right? So we use this big O notation to say that what is the error of truncation. When we truncate an infinite series to finite terms, we always skip something, right? Assuming that it is negligible. So when you neglect terms, what is the error or the order of the error that is associated? That is given as O of something, which is called the big O. We'll talk a little bit of that later today, and then we'll keep revisiting this stuff again and again. But your intuition is right. Okay, now, so we mentioned that for convergent series, if the series is convergent, right, that means more the terms, more number of terms you include, more accurate is your approximation. The leftover portion or the error portion reduces to zero, okay, if it is convergent. So that is what I've written. The more terms we take, more terms we take, the more accurate the function approximation becomes. Okay, in other words, as we go from, all right, so this is the punchline. If you look at the first term, it is a constant, right? Function evaluated at k. Please remember, on the left-hand side, we have a function. This is important, pay attention. On the left-hand side, we have the function as is, which has a variable in it. That means it is ready to accept any input variable. It is f of x. It is not a fixed number. On the left-hand side, it is a free function ready to take any value of x. That I have explained or represented as a polynomial. On the right hand side, yes, there are x also. Okay. F of k or f dash k, these are constant coefficients. Agree? constant fixed numbers. Okay. Now, if you look at the first term, there is no x. It is a pure constant. Okay. So if I represent the function with the first term only, that means f of x equal to f of k. Indirectly, I'm saying value of the function at any x is same as the value of the function at a. That sounds ridiculous. How are you saying that? I mean, this will change, right? If you change x, f of x should change. But I'm saying, no, it is always f of k. So you fix k. So you expand this series around x equal to k. Let's say k equal to 2, for example. So the first term would be f of 2. I'm saying f of x equal to f of 2. If I only take the first term, it will be this, f of x equal to f of 2, which is ridiculous. That means you're saying f of 5 equal to f of 2, f of 3 equal to f of 2, f of minus 16 equal to f of 2, right? So this part would be, if you take only the first term, it will be called as constant approximation. I'm saying f of x is equal to f of k. This will be exact only at one specific point. Where is that? F of x would be equal to f of k only at one specific point. In all other points, there will be errors. Where will this match? At x equal to k, exactly. F of k is f of k, but f of x, if you're saying is constant, obviously there will be error between actual and what you're saying, right? So the worst approximation is the constant approximation, where you're only including the first term, which is just a constant. There is no variability that can be modeled using a constant. There is no x, okay? Next, better approximation would be include two terms, the first and the second one. First term, second term. This is a linear approximation. Why linear approximation? Because on the right-hand side, you have a linear function, y equal to mx plus c. This is c, this is m, and there is x minus some kind of offset. That is fine, not a problem. But at least you have some um, some variability that you can capture on the right hand side in a linear way. So we are saying when x changes, f of x will take another value. The true function value would be something different. But you give me the new x, I can always approximate the new value of the function using this linear approximation. Given that, I have figured out what is the constant term and what is the slope term, and we can always find that, right? So this is linear approximation. Then comes quadratic approximation, when you include more terms, constant term, linear term, and a square term, right? So as you increase the number of terms, your approximation of the true function or the original function increases. You get more and more accurate values. Okay, now let's see this visually. Uh, okay. So what I've done here is I've taken e to the power x as my function. And this blue line is the true function, e to the power x, plot of e to the power x, blue line, okay? And I am using Maclaurin series, okay? Expanding, please remember, Maclaurin series is nothing but a special case of Taylor series where you are expanding the function at x equal to 0, okay? If you expand the function at x equal to 0, remember the expansion of e to the x, 1 plus x squared by 2 factorial plus x cubed by 3 factorial, blah, 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 blah. Okay. All the derivatives are at 0 is 1. If you remember, right? E to the power x derivative is e to the power x. No matter how many times you differentiate, it will be e to the power x, and at x equals 0, e to the power x will be 1. So all these derivatives are 1. This I have done to capture the Taylor series expansion, because all of these will be needed in the Taylor series. These coefficients are the corresponding derivatives divided by the factorial, right? So the first coefficient would be f0 divided by 0 factorial. 0 factorial is 1. Second coefficient a1 would be f dash 0 by 1 factorial. Correct? the A2 coefficient is f double dash 0 divided by 2 factorial. That is what I've written. Okay. Yeah, so this is e to the power x expansion at x equal to 0. Now, what I will do is start including these terms one by one. First, I will try to approximate it using the first term. Then I'll use 2 terms. Then I'll use 3 terms. And we'll see how the approximation actually looks like. Okay? Right now, n equal to 0. That means I have only included a0. a0 is 1. Correct? So if I go back to the expansion, we are using this expansion. Okay? First term is 1. If you include 2 terms, it will be 1 plus x, right? So first term is 1. My constant approximation of e to x is, I'm saying it is 1. Always 1. If it is always 1, then my graph of the polynomial would look like this. It's a constant approximation. It passes through 1. Everywhere it is 1. Okay? Are you with me so far? This is the true function. And this is the constant approximation because the constant is 1. Because first term is 1 in the expansion. Till now, is it clear? Okay. As you can see, this is the polynomial approximation. This is the true function. Both match at x equal to 0. The value of the true function is 1 because e to the power 0 is 1. Value of the constant approximation is also 1. It is 1 everywhere. So at x equal to 0, there is no error. Both match because it is expanded at x equal to 0. So it's designed to match at x equal to 0. The function definitely will match wherever it is expanded at. As you move away from x equal to 1, there you'll have errors. Okay. So if I go to, let's say, x equal to 1, now you see divergence. The true function value is somewhere here, which is 2.71 e to the power 1, that is 2.71. But I am saying it is always 1, right? So that you can see the gap. That's the error. There's some error. I've calculated some kind of percentage to show you the magnitude of error. If you move away further, there will be bigger and bigger errors. That means this constant approximation does not hold good if you move far away from x equal to 0. It's bad, right? Are you 100% clear with this? Similarly, you can try on the negative side. There is error on the negative side as well. The only place where there is no error is at x equal to 0. The approximation and the true function match exactly. Now I'll include another term. If I include the linear term, what will happen? E to the power x is approximated as 1 plus x. Only that much, correct? 1 plus x is a straight line. This is the plot. 1 plus x is a straight line, okay? This is the plot. One interesting thing that you see is this straight line is not just some arbitrary straight line. It happens to be the tangent to e to the power x at x equal to 0. It's the line that touches the true function. Okay, you know why this is not coincident. We have, see, in the constant term, we are only matching the function value. Okay, f of 0 will match with f of 0. With linear approximation, we are matching the function value and the first slope. Both are equal. If the slopes are equal here, then obviously the line would be a tangent. Same slope. Okay, so this one looks a little better. And if we move away, obviously there will be errors. But the error is less, only 26.42%. Okay, less error, 59%. Go back. Let me include another term. The next term is x squared by 2. Remember, 1 plus x squared by 2. It will be a quadratic function or parabola, you can say. So this 0.5 is basically half. So the polynomial reads like this: 1 plus 1 times x plus 0.5 times x square, or x square by 2. Now look at this approximation. Looks much better, right? Quadratic approximation. If you want to see the error, way less. Okay. So long story short, wherever the function is expanded at, the approximation will always match with zero error at that point. If you move away, the approximation becomes less and less accurate. But if you include more and more terms, then the error would be less. So that's the moral of the story. Okay, and you can keep increasing, increasing. I know you want to see. Oh, I have till 10. So this is beautiful, right? Practically the same curve. You don't, yeah. If so, so you already should feel that polynomial expressions are the easiest. You can handle derivatives very easily. Differentiation is no-brainer if it's polynomial. X square, x cube, x5, easy. And if you want to match a complicated function, e to the x is easy. Every calculator can calculate that in seconds. But if it's this function can be a massively complex function. Think of a valuation of a complex financial derivative. That is also a function. We can approximate that using polynomials. If you're working at a particular value of x, right now the market value of a of the input, which we say as call as risk factor, is something, right? You expand that function around that point and then forget about the function, work with the polynomial, because it will approximate it very well. If you move far away from that, so market risk factors have changed, then you update. Okay, so we'll see all of those slowly and steadily, but I hope this makes sense. All right, similarly, we can do the exercise for sin x. Remember the expansion for sin x? Sin x expansion is, let's go back. This is log 1 plus x. This is sin x. So what is the constant term? Let me ask you this. What is the constant approximation of sin x? 0. Perfect. Yeah. I mean, I didn't write 0 in the final expression because 0 is 0. But if you look at the constant approximation, the first term is 0. So your approximation of sin x, it is 0 everywhere. All right. Linear approximation would be sin x is equal to x. Okay. There is no quadratic expression because the second term is 0, right? But there is cubic. You can approximate this using a cubic polynomial. It will be x minus x cubed by 6, 3 factorial. So let's see how it does. Okay. So sin x is approximated as 0. So you see this line? This line is just the x-axis because y equal to 0. And it does a brilliant job at x equal to 0 because it is designed to do so. If you move away, approximation is always 0, but sin x takes some value. So there is some error, 100% error at the moment. Now if it keeps, changing because sin x is oscillatory, right? If I include more terms, so this is the linear approximation of sin x, which is x. Sin x is equal to x. So sin x would behave how y equal to x behaves. Y equal to x is just a 45-degree straight line. Why it doesn't look 45-degree in the graph is because the scaling is different. I mean, from here to here it's 0 to 1, but from here to here is 0 to 1. That's why you see it little skewed. But Yeah, you get there. So this is y equal to x, right? And here also, this one is the tangent to the curve. The best linear approximation to any curve is the tangent to the curve, because you not only match the values would be same because it is touching. You also match the slope. That is what we are doing to derive the coefficient in the first place, right? So this is the linear approximation. Then quadratic, nothing happens. Why? Because quadratic term is 0. So it is still that same linear expression. Then we take cubic. This is a cubic polynomial. All right. I did not do the experiment with error. You can feel it. I mean, it is coinciding with the curve. So it does very well approximation in this range. The range would be like minus 1.5 to all the way till, let's say, 1.2 or something. Yeah, or yeah, let's say minus 1 to 1. Between minus 1 to 1, if x moves between minus 1 to 1, and I'm using the cubic polynomial instead of actual sin x, I would still be fine. Look at the quality of the fit, right? And you can keep including more and more terms to get better approximation. Okay. Are you clear with what we are doing so far? All right. Let's do one more exercise. This time, we will expand e to the power x, but not at x equal to 0. We will expand e to the power x at, let's say, x equal to 2. So k equal to 2. Right? So we have a different, I definitely should remove this. This is not the right expression. Remember, when we expand at a different point other than 0, then all our terms would be x minus k square, x minus k cube, like that. Okay. And coefficient formula, you know. Okay. So I am not going through these coefficient calculations. We have the general formula. You can see, uh, yeah, the constant approximation would be what? F of k. Remember, approximation of f of x, constant approximation of f of x is f of k. So approximation of e to the power x at x equal to 2 would be, what is it? E square. That's the first constant term, correct? E square is, yeah, whatever it is, 7.389. And that becomes your constant line, constant approximation. Okay, remember e to the power 0 was 1. E to the power 2 is some 7 point something. Now this line does a perfect job at x equal to 2. It is designed to match the function at x, both coincide. But if you move away from x equal to 2, let's say we go back to 0. Function becomes 1, correct? E to the power 0 is 1, but the polynomial approximation is still at 7.387. And you can move. My buttons are not working, but that's fine. You can move away. There is some error. And if you want, so basically the whole story is, if you want to develop a approximate polynomial at a particular value of x, you expand the function at that x, and then start including more and more terms. That's the moral of the story. If you want to approximate the polynomial, the function at x equal to 0, use Maclaurin series, include more terms to get a better approximation of the entire function. Okay, so it will do justice to the movement around x. You'll not go that much wrong. If you want to do approximation at 2, x equal to 2, so let's say the market stock price is at 2, s equal to 2, and you are approximating the value of a derivative which depends on the stock price. Right now, s is equal to 2. I can use the value of the derivative, approximate the value of the derivative as a simple polynomial expanded around 2. So even if the stock price moves a little bit here and there around 2, I would still be able to approximate. So let me include more terms. You can see the linear term is again the tangent, but at x equal to 2, it's a new point. Okay. If you do quadratic, it looks like this, and the approximation keeps getting. So it tries to, adapt to the shape of the curve at that point, whatever you have chosen. Okay. Now this function is very, so after 5 terms, this function is very different from this function. This function and this functions are not same. Oops, sorry. It is shifted. Okay. So is it clear? Both Taylor series, Maclaurin series, visually what they are trying to do. All right, cool. I should probably take a break here. Let me see. Yeah, here are some of the visuals extract for your reference. Same thing I have given. This is for sin x. Okay, so yeah, let's take a break and then we'll talk about some more, practical applications of Taylor series. We'll do some questions on couple of valuations also. Not the, we are not there yet, but Taylor series treatment of a derivative value that we will also do. Okay, let's meet after 5 minutes. All right, now let's move on to some of the practical applications that we will be, using Taylor series for in quant finance. Question from some of Taylor series is used to approximate the actual function, yes, and also to approximate changes in function, both ways. Till now, what I've shown you is how to approximate a function, right? So if you have like log 1 plus x, you can approximate it using a polynomial. Where do you want the approximation to be effective? That is where you expand the function. If you want it to be effective at x equal to 0, you expand it around x equal to 0, include first term, second term, third term, how much you can. If you want the function approximation to be effective at another point, say x equal to 3, then you expand the function at x equal to 3 and include more and more terms. That's the whole idea. All right. Same infrastructure can modify a little bit to approximate the change in function, which is, I think, more uh, important from our practical needs perspective. So that is what we'll do next. Okay. So yeah, the timing couldn't have been better. You can use Taylor series expansion to approximate the change in a function. You just have to tweak the derivation a little bit. So let's say, yeah, one of the prime use cases of Taylor series is to approximate the change in a function when the inputs to the function change. Okay. Normally we understand if the input of function changes, then the function output will change. Okay. And that is predominantly given by derivative, just the raw derivative. That is the sensitivity, right? If x changes by dx, y will change by dy. The ratio is given by dy by dx. But that is applicable when the change is infinitesimal, extremely unimaginably small change. In real life, we don't have that kind of change. We have substantial changes, 1 basis point change, or stock price changes by 1%, right? It's not infinitesimal. So Taylor series comes in handy because it doesn't only involve with dx dy, it involves del x del y. The more terms you use, the better approximation you will get. So that's why you end up using not only the first term, sometimes the second term, sometimes the third term also. But practically speaking, we are pretty much content with the second term all the time. Okay. All right. So let's go through this. So when the input, yeah. In other words, if let's say right now x is x0, the current value of the input x is x0 or x naught. The value of the function is f of x naught. That's the value right now. When x changes to x0 plus delta x, so it gets shifted from the current value by an amount delta x. What is the new value of the function f of x0 plus delta x? Okay, that's our idea. So we're trying to find the change in value of the function if the input changes. Now the thing is, if you can evaluate this directly, then nothing like it. You don't need an approximation. Why do you need to approximate? So let's say x equal to 1. What is e to the power x? E. X changes to, say, 1.2. What is e to the power new x? 1.2. You don't need any, I mean, calculators or Excel, anything can calculate this value in milliseconds, nanoseconds, whatever. So you don't need an approximation for e to the x really. But in real life, you don't have functions like e to the power x. Sometimes that function would be a whole valuation engine, okay? Monte Carlo or binomial tree, something. And that is expensive. So in order to revalue the function again, this is called full revaluation. We'll talk more about this later on. But if you want to use that same valuation function at the new shifted input, it's called full valuation. That might be complex or complicated, computationally intensive. That's where Taylor series comes in handy, because now our function is a polynomial. Polynomials are not complicated. It's just a linear or quadratic term. That's it. And we use that to approximate the changes. Okay, so that's the story behind this. Now, how do we derive an expression for change in the value of the function? So let's expand f of x at x equal to 0. This is important because we are trying to approximate the changes around x equal to x0. So it makes sense to first write the expansion around x0, not at x equal to 0, but at x equal to x0. So here k is x0. Question from some, go ahead. How the Taylor series is derived? What do you mean? We just derived it. Do you mean some other equation? I think your question is related to what we are doing right now. Let me complete this. If you still have the question, let me know, okay? All right, so let's expand f of x at x0 because we're trying to approximate the change of the function at x0. So this is our expansion, f of x equal to f of x0 plus f dash x0 x minus x0. So k is basically your x0 at the moment. Oops. This expansion looks right. I have just replaced k with x0, that's all. Then value of the function at, so now, okay, here's the important thing. My function is now ready. My function is ready in terms of a polynomial. See this. This is my whole new function, okay? It is now converted to a polynomial function. Now, what is the value of the function at this new shifted x, which is x0 plus delta x? The value is given as, put this value in the variable. Please note that this is a brand new function, which is a polynomial function that is approximately same as the true function. This is what we have been doing so far, correct? And this one has the variable x intact, which can accept different values. This approximation is exact if x equal to x0. If you use a different x, then right-hand side will start to deviate from the left-hand side. That is fine, as long as, and we saw, right, if we use more terms and the changes are small, then it is okay. That is what we saw, right? So what we will do is, yeah, what is the value? So question is, what is the value of the function approximated by this polynomial? Well, what is the value you're seeking at? It is x0 plus delta x. Put that in the x. If you put that value in the x, you get x0 plus delta x minus x0. X0 get cancelled. So you get delta x. Similarly, in this bracket, you only get delta x square. I'll take a pause here. From this step to this step, did you understand what I did? Create a synthetic function, okay, which still has x, but now synthetic function is a polynomial function. And I use the Taylor series expansion to derive the coefficients, okay? Now that I have this function ready, an alternate, or you can say surrogate function, okay, which is supposed to be same as the true original function f of x. Question is, you're trying to revalue the function, right? F of x at x0 plus delta x. Okay, you already have x here. Use the surrogate function, the other function, uh, and find out the value by replacing x by the new value, wherever you want to value, right? And that is written so nicely that it gives me this result. Okay, if you understood this, finally, you take this one to the left-hand side. That gives you f of x0 plus delta x minus f of x0, which is nothing but the change in the function delta f. This is how much the output changed because x went from x0 to x0 plus delta x, right? And that is this. Is this clear, guys? It's just a two steps process. First and foremost, write the polynomial expansion for the function by expanding at the point that matters to me, which is x0, because I'm measuring changes there. So that is the first line. Second line, you want to revalue the function at a different point, which is x0 plus delta x. Okay, I don't know how to do that under the true function, or I don't want to do that because it is expensive. Instead, why not use this function to get that value? In this function, I have x. Wherever you have x, put this point that where you want to evaluate the function, and you get this expression. So this is my approximate value for the function at the shifted point. And then you take the difference, which is the change in the function, is given by this. Okay, I hope this is clear. Now, I use the same Taylor series expansion to approximate the change in a function using whatever I got. So this is how I can approximate the change in a function. Okay, I don't have to revalue. All right. There is a question, why derivative is not changed from x0 to x0 plus delta x? You are confusing a little bit. Once you get this, the derivative changes, but after I have done the step one, this function is frozen. Remember what we did in Excel? Okay, I have it here. So see this one. I expanded it for x at x equal to 0. I got this new kind of function that approximates e to the power x. If you want to evaluate e to the power 1, I'm saying do not calculate this explicitly. Instead, calculate this. Once you have figured out the derivatives of the function were used to manufacture this function, and your story ends there. Okay. At x equal to x0, you got your derivatives, and your function is ready to approximate. If you move substantially away from x0, then you have to recreate the function again. These sensitivities won't work. Right? Because sensitivities are the derivatives, because these are at x0. So anything near x0, this function holds good. That is what visually we saw, right? If you move substantially away from x0 to another new point, then you have to expand the function again at the new point. If it is close to x0, you can keep reusing this function again and again and again. Does that answer your question? So full revaluation is if instead of the polynomial, you're using the actual function to calculate the output. So instead of, so right now, let's say x equal to 0. E to the power x equal to 1. This is what I know today already. If tomorrow say x equal to 1, you can calculate the new value of the new function in two ways. Either you do e to the power 1, that will give you e. This is the complete valuation because you are using the original function to revalue. Instead, if I use this, that is called local valuation. Okay. So this is another term that we use, local valuation. Basically, I'm taking the help of the polynomial to find the value of the function. This is called local valuation. This valuation is, mark my words, locally faithful. This valuation is locally faithful. That means it will do justice to the valuation if your x is close to 0, because all my derivatives are manufactured at x equal to 0. So as long as your new x is in the vicinity of 0, this is faithful or reliable. I can approximate the change, the function. See, if you can approximate the new function value, you can approximate the change. Change is just the difference. It will work as long as x is close to 0, because my function was expanded at x equal to 0. So as long as the new x is close to 0, this is fine. But if it moves substantially away from after maybe 1 year, you should not use this function. Maybe x has become 3. Then you need to expand the function at x equal to 3. Okay. So you will use this stuff. F of 3, f dash 3 by 1 factorial x minus 3 for e to the power x. All the derivatives now will be calculated at x equal to 3 because the risk factor has drifted. The input has drifted substantially. I cannot keep reusing this again. I'll have to re-establish the approximate function. And then, changes around 3, this holds good. That's the whole story. Okay. So to your point, these derivatives will need to be updated once I move stuff substantially away from where I expanded it. Okay. That is the job of the front office. Okay. So yeah, we'll get to that later. Basically, see, derivatives are sensitivities. So they will release the sensitivities. Okay. And wherever you calculated the sensitivity today, that holds true if the x has not moved a lot. But if it has drifted a lot, then you have to reevaluate the sensitivities. Yes, you're right. So if there is a big change, then you have to reconstruct the polynomial. That's correct. If you reuse the same polynomial, we saw how much the error increases, right? If you move away from the point where you expanded it, the error keeps increasing. So if you still want to approximate using a polynomial, you have to re-expand it on the new value. Okay. So to summarize, full valuation is using the original function. That might be costly. Local valuation is using the derivatives and Taylor series expansion and using the polynomial instead to revalue the function. If x changes, don't use the true function, use the polynomial. That's local valuation. It is locally faithful because if x changes little bit in that locality, in that vicinity, my polynomial approximates the function very nicely. So I can instead use the polynomial. That is called local valuation, which is much faster because you are dealing with, just linear terms or quadratic terms, which is very easy. Okay, this is good discussion because it has a lot of practical significance. So yeah, we'll do a lot of practice later on. Hope that is clear. Now I ended up with this approximation. Question from Sachin, earlier question. Why Taylor series has only that form, summation of product of coefficient and variables upon polynomial form to approximate the actual function? I mean, polynomial is the easiest choice, right? If you want to represent any function by some other simplified function, your best, easiest choice would be polynomials. That's the starting point. Anything else it requires more computational power. Logarithms or trigonometric series, these are called transcendental functions. So puts pressure on the computation. So polynomials are the easiest. So that's why that's the choice. Okay, if there are other questions, let me know because we have spent a lot of time on this one. Let's proceed. We can talk offline if there are more questions. So we got this expression for change in a function, right? There are more terms, but for all practical purposes, we will not consider anything beyond this, okay? So till the quadratic terms we'll consider. So we'll just truncating the series after the second term, we get this expression. Note that this is the linear term, okay? And this is the quadratic term. Why? Because this has a power of 1, this has a power of 2. So this is the linear term, this is the quadratic term. Coefficient of the linear term is the first order derivative of the function. Coefficient of the quadratic term is half times, don't forget the half, second order derivative of the function. Okay. Yeah. So in practice, we typically work with the till the second order term, which provides sufficiently good approximation provided delta x is small, right? So we are working with small delta x. So you don't need to worry about cubic terms. Till quadratic, you should be fine. It's a good enough approximation. If delta x is large, then probably you have to move and then, I mean, delta x in one day will not be large. It will, keep cropping up. If you aggregate or consolidate for a year or something, then your x would have dramatically shifted to somewhere else. But you don't wait that long, okay? After a month, if you see the x has drifted a lot, then you reconstruct the polynomial or revalue the derivative. Your x0 is not x0 anymore. It will be, let's say, x1, the new level. And then find the derivatives and use this, okay? Yeah, most of the times we are even satisfied with the first term only, just this much. And why do we do that? This for mathematical convenience. I mean, if you can work with just a linear term, nothing like it, right? It's just proportional change. Tomorrow, if I tell you x changed by 2 units, if you know the derivative, first derivative, you will say derivative times 2 units. That's your approximation. Fast, easy, right? Lot of mathematical elegance is there. So yeah, and this term is the most significant one. This is an add-on, right, to improve the accuracy. In quant finance, right, when we work with derivatives, typically the left-hand side would be change in value of a derivative, because valuation is also a function. It's a function of different input variables. We call those input variables as risk factors, right? Option value is a function of the underlier spot price. There is interest rate, there is time to maturity, there is volatility. All these are risk factors or inputs. Okay. So we'll do that after we'll understand multivariable calculus, where we deal with multiple inputs. Today we are talking about a single input. Okay. So you can think of maybe bond value versus yield. There is an inverse relationship. If yield goes up, bond price goes down, vice versa. So yeah. So in financial context, left-hand side would pretty much always involve the change in value of a derivative. That is what you will deal with all your life, be it market risk or valuation or anything. Change in value of a derivative is so significant, right? You need to understand. So two things, value of a derivative and change in value of a derivative. Value of a derivative is all about pricing. Change in value of derivative is all about risk management. That is how I can distinguish between pricing and risk management. Pricing is about finding out the true value, one single point, what it should be based on different arguments. And then you think of, hey, how much it can change. Today is 100, tomorrow, what it will be. That is risk management, because it's all about future losses, how much a loss there will be in one day. And then you keep capital. Okay, so if I want to summarize, V is about pricing and delta V is about risk. And that's why in all of market risk, you deal with delta V, and Taylor series is the king. Okay, you use Taylor series everywhere for market risk. Okay, and these derivatives have special names in quant finance. So the first order derivative is called delta. Okay, and second order derivative is called gamma. And in case of bonds, we have special names. These terms get rebranded as duration and convexity. Duration is the first order change. Convexity is the second order change. That is bond lingo. But in general, we say for options, we have delta, gamma. Not just for options, you can also say like forwards. What is the delta of a forward? You can do that. Delta and gamma are more generic. Duration, convexity are specifically for bonds. Question from before, I noticed that most times we stop at second derivative and not consider higher ones. It's a trade-off between accuracy and practical convenience. Okay. So based on the magnitude of daily changes, which is delta x, till what term we can, work with, that gives us a good enough approximation and does not involve, if you go to cubic functions, then that becomes a little messy. So it's just a trade-off, okay, where you stop. You have to consider speed and accuracy, right? That trade-off is always there. All right. Let's do some quick exercises. These are practical, important exercises. So let's do this. I'll give you some more exercises. First one is the price of a zero coupon bond. So this is the first time we're looking at finance. We are not there, obviously, at valuation at this point. It is still, yeah, there are many more lessons that we need to learn before we attack the pricing problem. But doesn't matter. As long as it is a function, you shouldn't be worried, right? The price of a zero coupon bond maturing at time t is given by this. Don't worry about pricing. It's just a function. Left hand side is a function. Right hand side has some variables. Capital T is fixed. It is time till maturity. It is fixed in the sense at the moment today, right now, it is capital T. It is not changing. But with time, yes, the time to maturity will change. We are not bothered about that right now. Let's we'll consider that capital T is fixed. Y is the yield, right? Approximate the change in bond price up to the second order due to change in yield. So yield is changing, single input. What is the approximate change in bond price? And you want to approximate that till the second order. Okay. Another question from someone, is this valuation of derivative can be derived from Taylor series? No, valuation cannot be derived from Taylor series. Taylor series is used as a couple of things. For now, I can say that valuation is not, you cannot derive value using Taylor series. It is always used to approximate changes. Valuation will come from some other arguments, no arbitrage arguments, expectation, those things. Taylor series is used to manipulate some of the differentials. We'll talk about that later, not now. But yeah, to answer your question, Taylor series is primarily for approximating changes. So mostly risk management. Okay. So let's do this one quickly. Question one. So we're given this function v equal to e to the power minus yt. Y is the input variable, right? The yield. Please be careful when you write d versus del. Del is for any generic change, delta, right? Big, small, too big, too small. For everything, purpose, you use del. When del is very small, it becomes d. This is called difference. Difference is a generic word. This is called differential, which means all the changes are small, very small, infinitesimal. Okay. In Taylor series, we use delta. Change in value of the derivative or the bond is equal to, what should I write? First, we write the Taylor series expansion, the change formula. change in value of a function is at any point. Okay. So derivative times delta x plus half second derivative delta x square. So right now the yield is, let's call it as y. And yield changes by a small amount delta y. What will be the change in value of the bond? So I can write delta v is equal to derivative okay, times delta y. Please note the difference. We have dv by dy here because we are actually calculating the derivative. It is the derivative, it is not delta. This term, which is the slope, is the derivative, multiplied by whatever, how much amount is the input is changing. So here the yield is changing by delta y. This is a generic change. Okay, it's small, doesn't have to be infinitesimal though. Okay, plus half double derivative. I can write d square v by d. Either way, I mean, this is fine or this is fine. Delta y square. So this is my quadratic approximation of change in bond price because of change in yield. Okay. All I need to do is find out these derivative. What is dv by dy? dv by dy is e to the power minus yt times minus t, and second derivative e to the power minus yt minus t times minus t, which is t square. Now I just replace. Change in value of the bond price because of change in yield is equal to minus e to the times t times delta y and plus half Is it clear? Does this look good? Okay, cool. I can do something else. This is the beauty of having exponentials because it keeps reoccurring, right? This e to the power minus yt is the original v because the original v. So minus v t delta y half v t square delta y square. I can take v to the other side, which gives me delta v by v is equal to minus t delta y plus half t square delta y square. Okay, this is neat. Now, those who are familiar with bond pricing a little bit, I'm pretty sure all of you are a little bit. On the left hand side, we have the percentage change in bond price because it is change in value of the bond divided by original v, that is the percentage change, is given by linear term which is multiplied by t. This is called as duration. To be more specific, this is actually modified duration. But here is the thing. Let me ask you this. What is duration? Do you know? For bonds, what do you mean by just duration? Plain vanilla duration. What does it mean? What is the interpretation of duration? Price sensitivity comes a little later. It is related to duration, yes. But it is not the plain duration. Middle says maturity. Macular duration, yes, yes. Time to get money, that is correct. Duration is the average waiting time to get all the cash flows. Because for, let's say we have a coupon bond. For a coupon bond, you get coupons in a periodic intervals, and then at the final maturity, you get the principal. So you're getting different cash flows at different times. One natural question to ask would be, hey, what is the average time to receive all the cash flows? So you weight all the cash flows, actually PV, present value of the cash flows, with the respective time of arrival or time when they flow to you, divided by the total value of the bond. And that gives you a time figure. That is the weighted average time to receive all the cash flows. That is called duration. In case of a zero coupon bond, there is only one and only payment. And that is happening at maturity. So the duration, plain duration of a zero coupon bond is T, time to maturity. And the same one comes here as well. In the second example, we'll see that the term that comes here is a tweaked or modified version of the duration. But if, please remember this, if you're using, what kind of compounding is this? If I'm using this formula, what kind of compounding? Is it discrete compounding or continuous compounding? Continuous compound. In case of continuous compounding, plain duration, macular duration is equal to modified duration. There is no adjustment. So that's why you see, all of you understand T is the duration of the zero coupon bond because there's only one payment happening after T. So your waiting time, average waiting time is the same T. And the same macular duration is the modified duration as because it appears as a coefficient to the change in yield. We know this has to be the modified duration or the sensitivity. They are same as long as you use continuous compounding. If you use discrete compounding, the formula would be different. We'll see that in the next question. So this is the first term is duration. That explains, that is a linear approximation. So duration gives you a linear approximation to the change in bond price, actually percentage change in bond price. Okay, it's a linear approximation because just give delta y, it will multiply and give you the value. And there is a correction term. This half times, this is called convexity. In regular world, it is called gamma, but in case of bond, it is convexity because it gets multiplied with change in yield whole square. Okay. And one thing you note here is this has a sign, minus sign, and that shows inverse relationship. If delta y goes up, delta y v will go down, and vice versa, inverse relationship. Okay. But if you look at the second term, delta y whole square. So that means if delta y is positive or negative, it doesn't matter because it's always whole square. So it'll always be positive. Okay. So if you are holding the bond, if you are a bond holder, then convexity is your friend. Convexity will always help you. It gives you a cushion. So whatever is predicted by delta y, you'll get something additional always. It favors you. Convexity is your friend. If you're the bond holder, convexity is your friend. Okay, same thing for options also. When you see options, the gamma component helps if you're the option holder. Does not matter call or put. If you hold the option, then gamma helps you. Okay. It is always a positive lift, right? So that's why. Irrespective of the sign of delta y, positive or negative is always positive. Anand has a question, how do you get V on the left-hand side as a denominator? No, so take this V common and take it to the left-hand side. Remember, e to the power minus yt is the V, original V, which reappears. So just take common and take it to the left-hand side. Did I miss any other question? Sambhav says, just as a quick refresher, can you explain MAC duration and effective duration as one-liner? One-liner, I had the exercise. Let's do the second exercise. So it'll be clear there. Okay, so this is a fundamental relationship. We did it for a zero coupon bond. Let's do it for a general coupon bond, which is the next question. Price of a T coupon bond with face value F and annual coupon payments at the rate C%. Okay, it's not, the coupon rate is C% annual, keeping things simple. Under flat yield curve, I know I'm throwing a lot of financial information, but it is fine. The point of this exercise is to use Taylor series. At the end of the day, it's just a function, right? So this is the valuation formula for a coupon bond. Face value times C% is the coupon rate. This is the coupon that you keep getting until the end of maturity. They get discounted by the respective discount rate. If you discount it like this, it is not, the yield curve is not continuous compounding. It is annual compounding, right? This is the last coupon, and then you also get the principal back that gets discounted by 1 plus y to the power t. If this is the function, approximate the change in bond value up to the first order because of change in yield. Second order also you can do, it'll be messy. Okay, so let's not do that. I leave it as an exercise for you. Okay. Question 2, we have a new function, coupon bond. This is not zero coupon, this is coupon bond. First coupon, second year coupon, right? Final coupon and the principal back. What is dv by dy? dv by dy is minus fc by 1 plus y square, not plus, minus 2fc divided by 1 plus y cube. Shouldn't write plus, it should be minus dot 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 dot. This one is minus fc, wait, minus tfc, not kfc, okay? T plus 1, and again we have minus tf 1 plus y to the power t plus 1. Okay. Now what do we do? This starts with a square directly, right? Let's take a 1 by 1 plus y common. fc by 1 plus y. Let me write 1 times fc, okay? 2 times fc by 1 plus y square. T times, let me take this common, f times 1 plus c divided by 1 plus y to the power t, because we have taken 1 plus y common. Now, if you look at the expression in the bracket, first coupon discounted. So this part is the PV of the first coupon multiplied by when does it come to you after end of 1 year, PV of the second coupon, second cash flow, multiplied by the time when it comes to you. PV of the final cash flow, which is principal and coupon, multiplied by the time when it comes to you. This part is the weighted sum of all the cash flows. Okay, weights are the PVs and multiplied by the respective times. I will do this. I will multiply a V and divide by the V. V is sum of all the PVs. So if you add this plus all of these plus this, that's the V. Okay, so separate cash flows, PV of cash flows weighted by the respective times divided by the sum of PV of the cash flows. That's the definition of any weighted average. This is how you do weighted average. Okay, you multiply the weights, then divide by sum of weights, and you get the average weighted average of something. Here, what are we averaging? We're averaging the time average waiting time for the cash flows. So multiply V divided by V. If you do divided by V, this becomes the duration. Okay. So my dv by dy is is very nice. So that, I mean, the idea of duration is average waiting time, but somehow magically it also surfaces in the derivative. So that is a happy coincidence. Okay. Now I write Taylor series expansion. Delta V is first order derivative times change in yield. Please do justice to D and delta when you write this expression. Okay. That is important. There is no second order. I have not, in the question, I have said specifically approximate till the first order. So this is the first order approximation. And this is equal to minus V by 1 plus Y D delta Y. Now to make things little more neat, these guys started calling this stuff as D star minus D star delta Y. So your final expression, whoops, not this much, apologies. D divided by 1 plus Y is called D star. So there is still a V here. We rewrite this. P times D star delta Y. D star is D divided by 1 plus Y. Okay. Now D is called the maculae duration, which is the average waiting time of receiving all the cash flows. D star is called M duration or modified duration. M stand for modified. Modified the duration. So that is just one number, right? And this is the sensitivity. It's not the true sensitivity. It's basically the, yeah, if you take delta V by V, then you get D star delta Y. So it relates to the percentage change always. Remember, in case of bond, it is always the percentage change. It is not the absolute change. Or you can say relative change. And that's your derivation for change in bond price, how it relates to the duration and modified duration. Okay. Yes, that is what I was coming to next. Thanks, Devdatta. So this is for annual compounding, right? If you have like a semi-annual compounding or quarterly compounding, or for that matter, the compounding frequency is m times per year, right? Then your D star, this is the general formula, is D divided by 1 plus Y by M, where M is the compounding frequency per year. M is the compounding frequency. So for semi-annual, it will be D divided by 1 plus Y by 2. For quarterly, it will be 1 plus Y by 4. One interesting thing, if this stuff happens, this indirectly means what? If you're compounding infinite times per year, what does that mean? It's not daily. No, 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 no. I mean, well, practically you'll do a daily calculation, but this is continuous compounding. Continuous compounding is much, much faster than daily, unimaginably faster, okay? If m tends to infinity, what happens to this guy? Y by infinity? Y is just a number. So a finite number divided by infinity is 0. So you get, so that's why in our first exercise, we saw the same D appear here because it was continuous compounding. I would recommend try this exercise with continuous compounding. Take e to the power. Do two exercises you must do. Okay. One is for actually you can do only one, m compounding frequency, and try to derive this expression. This is a very good exercise. Okay. All right. I hope this is clear. Now, this is a very fundamental application of Taylor series to a finance problem where we are concerned with change in value of the derivative or the bond. There's another question. Modified duration means you are discounting weighted average time. Discounting weighted average time, I didn't get that. So if you see this, D is your macular duration, which is the weighted average time. It's just a time. So let's say if it's a 10-year bond, your duration would be like 7 years or 7.2, something like that. And then in the expression of delta V, D appears with divided by 1 plus Y. Okay. So we are calling D divided by 1 plus Y as D star. But inside of D, all the time and waiting and everything is captured. So, oh, you're saying discounting duration by yield. I mean, yeah, you could say that, I guess, because it is D divided by 1 plus Y. Yeah, I've never thought it like that. Could say that. But be careful with the different compounding frequencies because we have to do 1 plus Y by M if it is not annual. All right, cool. Let's proceed. We should, let's go a little faster. Okay, I think couple of slides. Yeah, all right. So in order to find derivatives, there are two choices. I'm talking about how do you find derivatives? There are two choices. One is analytical derivative. So there you just do the differentiation using some formula. So let's say you have e to the power x. What is the derivative? You know it is e to the power x. That is the exact analytical derivative. Okay. Sometimes your functions would be complicated. As I said, right, valuation functions. It could be a whole different engine. But in general, you can use numerical approximations to approximate a derivative. I'm not talking about Taylor series here. This is just how do you calculate derivative of a function if the analytical differentiation does not exist. Okay. All right. So at the end of the day, dy by dx means what? Change in y by change in x, delta y by delta x, provided delta x is small. That's the definition of derivative. So why not use this definition to calculate derivative? So what we'll do is change x a little bit by delta x, see the change in y, and then take the ratio. That is called as finite difference. Okay, because you are shocking or bumping up the input by a little bit by a finite amount. It's not infinitesimal anymore. It is a finite amount, like 1 basis point or 1%. And then measure the change in y, take the ratio. Will that be the exact match with the analytical derivative? Of course not. There will be errors. But it is an approximation. Okay. So it's called as finite differences. And there is a whole different pricing algorithm or pricing engine using finite differences, which is extremely fast and popular. That is something we'll cover in detail later. All right, now there are two sensitivities we're dealing with, right? One is delta, which is the first order derivative, and then there is gamma, which is also called as convexity. So how do you approximate the delta sensitivity using finite difference? Okay, which is the first order derivative, dv by dy or dv by dx. How do you approximate using finite difference? There are three different choices available. One is called forward delta, another one is called backward delta, and then we have a third choice called as center delta. So here is the expression and the visual. Forward delta is very simple. Shock the x positively. Okay, basically you adjust x upwards. You give a positive shock to x and then measure the new y minus the old y in the numerator. So if I want to rewrite this, it will be f at the new value of x minus f at the old value of x divided by new value of x minus old value of x. X gets cancelled. Yes, change in x is delta x itself, right? So If you write it in this fashion, it is called forward delta, because x is being, so forward means you think of moving x going on the x-axis, you're moving from left to right. So moving forward, okay, in this direction, that is forward delta. Graphically speaking, so let's say this one is the true curve, the function that is in context, f of x. This is the plot of f of x. I want to find out the derivative at this point. So at x, the value of the function is here. The true derivative is given by the green line, which is the tangent. So slope of this tangent will match the derivative of the function. It's the actual true derivative, right? If I cannot calculate analytically, I have to approximate using finite difference. Now we're doing a forward delta. That means shift x to x plus delta x. Delta x is positive. At this point, my function value would be here. Then you calculate just the slope, change in y by change in x. This is the change in y, and this is the change in x. Right, so this is the change in y, this is the change in x. If you take the ratio, it will be the slope of this line, the blue line. Okay, so that's the forward delta. We can do a couple of quick examples in Excel. It's no brainer, but you can see that there is some error. Look at the green line and look at the blue line. They don't have the same slope. There is some error. I mean, they're close, but there is some error. Okay, now let's talk about backward delta. Again, remember, I'm all the time I'm trying to approximate the derivative at this point x. Delta x is up to me. I will choose that shock amount. Smaller, the better, right? Backward delta, you're moving to the left. So you start from here. So this is my original value. I move to the left. At this point, the new value of the function is here. And then the line joining these two would be the line that will give me the slope. Or you can say change in y is this much, change in x is this much. And the ratio of these two would be your estimate of the slope. Backward delta, you can write backward delta in two ways. One is, I think the more natural way is this. New y is this minus old y. See, remember, we are shocking the x backwards or to the, shocking it down. New y minus old y divided by change in x, which is new x minus old x, right? So in the denominator, it actually is, it's minus delta x. So you sometimes you see this form, or change the order in the numerator and keep this one positive. Same thing. Instead of writing this first, you write f of x minus f of x minus delta x divided by delta x. This is called backward delta. And you can see the divergence between the green line and the blue line. It's a little different, right? And then we have something called as center delta, which is, combining both ideas. Take a forward step and take a backward step. Take the difference divided by the total change. So you can clearly see, it combines two steps, right? So one point is here, x plus delta x, the value of the function is here. Another point is here, x minus delta x, the value of the function is here. And the total change in x is 2 delta x. That's why change in y by change in x. And that's this blue line. You can see graphically at least that it does a much better approximation of the true slope. Look at the green line, look at the blue line. They are parallel, almost parallel. Parallel means same slope. This is the change in y and this is the change in x. Okay, so center delta is definitely much better in terms of accuracy. But at the same time, who can tell me what is the demerit of center delta? We can see the merit definitely. It looks like more accurate. I will prove this using Taylor series in five minutes. But is there any downside to center delta? Anyone? Tangent, can you elaborate? Um, it is, yeah, Arjit says it is twice delta now. Yes, so that's the reason. It requires two valuations. Okay, requires two valuations. In forward delta, backward delta, right now the value of f of x is known. You don't want to do anything. You only want to revalue the function at one new point. Either it is f of x plus delta x or x minus delta x. In case of center delta, you need to evaluate both. That brings in additional complexity in terms of calculation, right? So if you want accuracy, obviously you have to sacrifice some speed. That's always there. Speed or accuracy. This is more accurate, but you need to evaluate f of x twice at the two, shocked points. That's center delta. Okay, now I want to quickly give you the proof using Taylor's. Why I brought this topic is because you can explain why center delta is better compared to backward and forward delta using Taylor series. Uh, yeah, let's go through the derivation. It's very easy. So remember, we can approximate we can value a function at any x using our Taylor series expansion. Okay, this is k. Okay, f of k. X0 plus delta x, or you know what, let me not confuse this one. Let's go back to the change equation. See this expression we derived? F of x0 plus delta x is f of x0 plus derivative at x0 times delta x and blah, 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 blah. So I'm using the same expression here. Okay, there are some more terms that we did not see in that, but these are all natural, right? First derivative times linear change, second derivative divided by 2 times quadratic change by 3 factorial cubic, etc., etc. For forward delta, we are saying it will be this expression, right? At the function value at x0, which is f of x0. You want to find out the derivative of the function at x0. So essentially, this is what you want to calculate by using finite approximations. So forward delta is shock x0 by delta x positively minus the original function divided by delta x. In this expression, you can do that. Take this one to the left-hand side. And then in the remaining portion, divide by delta x. That will give you this on the left-hand side. On the right-hand side, it will be, look at the first term. Delta x will get cancelled. You're dividing the whole thing by delta x. So take this one to the left-hand side and divide by delta x. We get this. Second one square will disappear. You'll have 1 delta x. And then from cube, you'll have delta x square, like that. Okay. Now, this expression is f dash x0 plus a bunch of terms. Okay. Now, if delta x is small, this is the biggest term. And these ones will keep getting smaller. So if you consider this part, which we are ignoring, so basically we are saying, so if you see this, right, forward delta is approximately equal to the true derivative of the function at x0 plus some other error terms. There are some additional terms that come, as part of this finite approximation, you are bound to have errors. It will not be an exact approximation of the analytical derivative. Based on your choice of delta x, you will incur some error. These terms will contribute to the error because you are saying the left-hand side is the true derivative, correct? It is the true derivative plus something else. That's something, we are trying to measure the order of this error. Now I was saying in this error term, which is left out, delta x is the biggest term. delta x square will be much smaller, because imagine delta x is just fraction. It's a very, very, very small number. If you square a fraction, or to cube, those will become smaller. So we say that this entire error term is of the order delta x. Whichever is the highest term, that would be the order of the error. Okay. So yeah, it's of the order of delta x. So we write that forward delta is the true delta plus some error. That error is of the order of delta x. So whatever delta x you choose, so delta x 0.001, overall error would be in those, so let's say let's you choose delta x as 10 to the power minus 4. The total error will be of the same order. So it could be like 1.2 times 10 to the power minus 4 or something like that. This 10 to the power minus 4 is the order. Okay, the order of the error is delta x. Same size of delta x. You can think like that. Okay, same size of as delta x. So if you choose a bigger delta x, accordingly you will incur that much error. Okay. All right. Now let's use another equation. So instead of delta x, I use minus delta x. Just replace delta x with minus delta x. Same equation, replace delta x with minus delta x. Left hand side is this. Right hand side, just, instead of, so here I had delta x, now I have minus delta x everywhere. Backward delta is defined as this, again, take it to the left hand side, but divide by minus delta x. Okay, this is this definition. Divide by minus delta x. So what will happen on the right hand side? First term is again f dash x0, because divide by minus delta x will cancel this term. Then it will be minus delta x. Okay, because this will be delta x whole square, positive. Then you divide by minus delta x, so it will be minus delta x. This will be minus delta x whole cube, because it is cube. You divide minus delta x, it will be delta x square, positive delta x square. So it will be like this. And you can see this is backward delta, right? Backward delta approximates the true derivative f dash x0 plus some error term. The highest contributor to the error is delta x. So this error is of the size delta x again. The order, so Sachin was saying big O notation, right? This is big O notation. It is used to express the order of the error. So these are of the same quality, okay? Forward delta has the order of delta x. Backward delta also has the order of delta x. Now let's talk about the center delta. How do we calculate center delta? So this is equation 2. This is equation 1. Now there is a typo. I will correct this. So this is plus. Subtract 2 from 1. So if you do minus this, okay, what will happen is, let me use another ink, it's becoming a little cluttered. This will get cancelled. F dash x0 times delta x minus minus this guy will be 2 times f dash x0 delta x, because there is a minus sign here already. I'm subtracting equation 2 from equation 1, okay? So these two get cancelled. This will be doubled. This and this will again cancel, because positive delta x square, my negative delta x square is the same thing. It will do minus, this will cancel. This minus this will be double of that term, double of this delta x cube. So even terms will cancel out, odd terms will be doubled if I do the difference, okay? And then finally, so you do the subtraction, then divide by 2 delta x. So let's see what happens. First term is 2 f dash x0 delta x. Second term, this term vanishes. This term is 2 f triple dash x0 by 3 factorial delta x cube, right? If you divide by 2 delta x, 2 delta x goes away, you are left with f dash x 0. In this term, 2 delta x goes away, you are left with um, f triple dash x 0 by 3 factorial times delta x square, correct? Because 1 delta x will get cancelled. And we don't need to worry about other terms. So here you can see that this one approximates the derivative plus the error is of the order delta x square. Delta x square. Now you tell me which is smaller, delta x or delta x square? Delta x square, because it is a fraction. Delta is a fraction. So that's the reason why center delta provides a much better approximation, because the error is of the order delta x square. Okay. All right. We can do a quick example in Excel if you have time, or I'll leave it to you. You can calculate the second order derivative approximation also using finite difference. And for that, interesting, you know how you calculate that? You add equation 1 and equation 2, and this is what you get. So let's see. F of x0 plus delta x plus f of x0 minus delta x is equal to 2 f of x0. This term and this term will cancel because f dash 0 x0 delta x, this is f dash 0 x0 minus delta x. This will cancel. We're just adding these two series. If you add, the first term would be 2 times f of x0. This will come. Second term, linear term will cancel. Quadratic term again will be doubled. 2 times um, 2 times whatever. We don't need to worry about this actually. So this is what we'll get. 2 times f of x0, 2 times this. All the even terms will come as twice if you add these two. Okay. Now take this one to the left hand side and do a divide by delta x square. Okay. That gives the approximation for this guy, because 2 and 2 factorial gets cancelled. Okay. So this is our gamma, right? So you can approximate the second derivative of a function by using this finite approximation. There are other forms also, but this is the most popular. Okay. So how do you do this? It's very easy. Shock the x upwards, revalue. Shock the x downwards, revalue. Minus 2 times the original value divided by the shocked amount whole square. And this definitely requires two valuations. You cannot escape it. For gamma, gamma is costly because you at least need 2 valuations if you're using finite difference. All right. Yeah, that's all I had. Any questions? So this gives you a proof. This is the visual proof why center delta is better. This is the mathematical proof based on the order that we can see that center delta has a less uh, order of the error. And this is for gamma. Any question, folks? We'll do lots and lots of exercise and derivations going forward. But I hope you found this useful and you can appreciate the power of Taylor series already. Okay, I will leave you guys. Thanks for your time. I'll share the assignment in a couple of days.